Might not be bad. Yes, you can try that. Right. So you have a finite dimensional vector space, let's say over R, and yeah, okay. So let yeah, let's just write the title maybe. So equivalence. Just a minute. I should just turn on my video. Equivalence of norms on uh, a finite dimensional vector space. Yes, that's right. And also, in fact, uh, actually, that's the equivalent that if any sequence is Cauchy in one, then it will be Cauchy in the other. Yeah, but yeah, I mean, if there are two metrics which have the same Cauchy sequences, that doesn't imply that the norms are equivalent or metrics are equivalent. So that you can find a counter example for that. But yeah, let's try to prove that this is an interesting fact. Yeah. So, hmm, okay. Yeah, let's just say norm one, norm two. Yeah, by the way, I should just mention, I mean, I should just write here that V over R. C also works, but yeah, alpha beta greater than 0. X. Right, so this is an equivalence relation. Yeah, okay, so yeah, so let me write the, so, uh, sorry. So we want to show all norms are equivalent, so that's probably clear. That's the problem. So the plan or the goal, or maybe the strategy or whatever. So the plan only. Plan is that uh, show that every norm is equivalent to the two norm. So how do I write the two norm? Right, but by two norm, what do you mean? Right, that one, yeah. So let's not write that here then. Yeah, we can say A and B. I just put this and dash or something. to the 2 norm. Okay. Hmm. Right, but you need to show that all norms are equivalent. Yeah. Yes. So that is where maybe uh you can use topology, things like that. Yeah, so let's write that. Norm is a continuous function. Any norm is a continuous function. Yes, that will also come. So I think you can just try to look at this. Let's see if this works. So, so these are two arbitrary norms, and you look at this function. Okay. Now, f, you can think of f as a function from V, but you can also think of f as a function from the unit sphere of V. Be- yeah, and that is because these norms are, yes, yeah, they're homogeneous. So that's why this function can equivalently be thought of as from the unit sphere. So, right. Yes, exactly. Yeah, that is what, yeah, unit sphere to r greater than 0. So this is a continuous function. So now you can use extreme value theorem. But you have to, yeah. But what do we need to apply the extreme value theorem? We need to show that this is a compact set. Like you have unit interval, here you have to show that it is compact. So, but how do you show that that the sphere is compact? So is this this statement? What is the state? Can you state the problem once again? Uh, okay, but yes, I think we should. But we should also mention that given any two norms um, that induce the same topology as that on Rn, that should be, yes. Because if, okay, so if we assume that, so let's do that and then we can do the other case if that case is true. So assume that this and this both induce the usual topology. And usual topology means the balls are the unit, the usual balls in the two norm. uh, so uh, I mean, like, I'll give you an example. For example, if you take the two norm, then the unit circle is this. And if you take the one norm, then right, it's this. Correct. But these two are inducing the same topology. Even though the unit ball here is not a ball, but still this is they are inducing the same topology because you can put a so conceptually the reason is because you can put a smaller ball inside this and you can put a smaller diamond and so on. So that's right. Yeah, of the different topologies, right? But 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 also in some sense I am already assuming that that can be done when I say that they are inducing the same topology. Okay, but still it is not. But still it is not always true that the norms will be equivalent. In this for finite dimensional vector space, it is true. Otherwise, it is not true, even though the topology is same. So there are two things. The topologies might be same, but the metrics might not be equivalent. But in this case, they are saying that if the topology is same, then the metric is also same. But anyways, let's just complete this. So this implies that SV is compact because in Rn the unit sphere is compact because closed and bounded. So that is something. And that implies that F has a minimum and maximum. That's right. Yeah. That's it. But then I don't know what about the other case. If the topologies are not same, I do not know if there is a unique topology on. So let's just look at Rn. This I have never thought of. Rn. Let yeah. Let this be two norms. Question is, are they induced? But just before we look into this question, there is, I think, a better question to look at, which also solves that problem. Let this be a norm on a finite dimensional vector space over R is SV, that is a unit sphere, so that is just X such that norm X equals to 1 compact. If this is true, then we don't have to prove that. Then we don't have to assume that the topologies are same. Use this. Exactly. So let us see if this is true. This should be true. Okay. But let's try to prove this. Yeah. So this V is V. You see, so the only thing that we have to ask is V complete? Is V a complete metric space? So the metric coming from the norm, is V a complete metric space? Why am I saying this? Because okay, yeah. So why am I saying this? Yeah, because you see, if it's complete, then you can prove that uh, the unit ball SV is totally bounded. Okay, then it will be compact. But the totally bounded will come. But first, let us answer this: is V complete? Or we can directly answer the question. Yes, 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 yes. That's right. Yes, yes. You can think like that. Yeah. Then from there you will get the compactness. And we must prove this anyways because I think that it should be equivalent. Yeah. But yes, if you have it, if you have a nested property, you can. Yeah, you can. Yes, okay, okay. Right. That's right. And CI is closed. All right. Mm. Yeah, so you're saying that this is the same as Cauchy sequences converge, or Okay. Yes. Right. So from wait, so yes, that makes sense to me. Yeah. Okay. So the nested interval theorem is same as every Cauchy sequence converges. Right. Yeah. And maybe here we can just say that this is a single point. No, because the diameter goes to zero, so it should be. I think I don't need to say that. It will follow because the diameter is going to zero. Yes, right. Yeah, if there are more than one point, the diameter cannot be zero. Yeah. So that's right. Okay. I mean, I don't know. This is a formulation of the problem. Mhm. Yeah, this might not be true, I think. Or I don't know. Yeah, might be true. Sorry. Because you see, the problem that I'm having is that if even if you just forget V and take V equal to R itself, right? Then uh, is R complete with respect to any norm? I don't know. E- so R as a set. So you take R as a set, not with a topology. Okay. Because yeah. So yeah, and it doesn't hold for any norm. That's true. You need finite dimensionality. Okay. Uh, yes, exactly. That's the same question, right? And on any norm, and that question I do not know because so R you're going to think of as a field and not with a topology. Okay, because we need to forget the topology because we are going to put a norm which can have any topology. Okay, and then I don't know if it's going to be complete or as you're saying have the nested interval with that norm. Yeah. No, but I think there the assumption is that they induce the same topology because when you say that all norms on R, then you're already thinking of R as a topological space. I think that's in the statement. It I might be wrong. It may not be. Then we are done. But at least what we proved, our proof, which obviously includes a proof of V equal to R. There we assume that the sphere is compact, and that follows if the topologies are same. But if some mysterious topology is there, I don't know that. Because, like, for example, if you take the integers, the integers are complete with respect to the norm coming from R, the usual norm, because that makes Z a discrete space. Okay, if you take the usual norm, then it's complete because you get the discrete space. But if you put something like a p-adic metric, which is like, which is basically, as you know, like the norm of a number, of a norm of an integer n will be something like this, or or yeah, the highest power of prime, that p, fixed prime p, and the highest power of the prime p that divides n. This is also a norm. But if you put this norm, then Z is not discrete and Z is not complete also. Yes, right. And because you have one p to the n, that's a Cauchy sequence then. That goes to zero, but okay, I mean, zero is there, but yeah, you can get counterexample. It's not complete. Yes. So that's like an example. And so I don't know what happens if you, I mean, I don't know how to put p-adic metric on R, but on Z, I gave you a counterexample. Yeah. But again, Z is not a vector. But then vector space condition might make things nice. I don't know. Interesting. But then it may still happen that the spheres are still compact. Because again, the sphere is just 2 points then. No, no, the sphere, what is the sphere? Z, if you take Z with the p-adic metric, huh, right. So the integers are a co-prime. Is that a compact? Right, that's right. So n such that n and p is 1. Is this a compact set? Because this is the sphere. Hmm. Mm-hmm. Yeah. But it means that you do have, well, let's write it here. So you do have Cauchy sequences. So let's look at the sphere on Z with the p-adic metric. Yeah. Yes. So as you're saying, so So let's say P is right, but it, yeah, so you can have like 2 plus P, 2 plus P square. Let's say P is not equal to 2. And this is the Cauchy sequence. And does it converge? That is the question. So is clearly Cauchy. Yeah. Hmm. Yes. Yes, yes, right. And so that goes to 0. So it is Cauchy. Yes. But it also converges to 2 basically, right? So it's also convergent. So we should think of some other example or 2. Like one other way, one other example, not example, but oh wait, this is a unit sphere, right? Yes, so this is a slightly uh, non-constructive viewpoint. So if you take Z, Z is not Z with a p-adic norm is not complete. Okay. So if you take its mm, no, that is not, no, sorry, that is something else. And there it is actually complete. It's quite interesting. Yeah, so maybe I should mention the interesting thing. So if we take ZP, which is the completion of Z with respect to the p-adic metric, okay, and then you take Q. Yes, yes, yeah. R is, yeah, exactly correct, exactly. Then similarly, you can take Q and complete it with the p-adic metric. You get this QP. Okay, now right, you get this QP, and again this will sit inside this. You can prove that. Then it turns out that the unit uh, but there it will be true. Yeah. But if you look at the unit ball, not the unit sphere, if you look at the unit ball of QP, that is actually ZP. And there is a theorem which is not difficult. It shows that uh, there's a theorem that says that ZP is actually compact. So right. And what I wanted to say is like, so this QP is like your R, because Q is like your Q, and you complete it with the normal metric, usual metric, you get R, but complete it, now it's QP, right? So this is like an example of a strange metric. Okay. But still, if you look at the unit ball, it is still compact. And hence the unit sphere is also compact because it will be a closed subset of a compact set. So that will imply that the unit sphere is also compact. But this is just like facts. We have not able to. I don't know if this unit sphere um, should be compact. Can you deduce it from these things? ZP is compact, but that doesn't mean that this will be compact. Exactly. That's right. Yeah. It will not be right. That's the point, right? Because you see, yeah, this Z, this thing sits inside this, right? Now unit sphere in ZP is actually there are many more points. Right. So the answer is no. And as you said, it's based on that idea. So if we just take the unit sphere on Z, this will of course sit inside the unit sphere of ZP, right? So then this is compact, but also this is not everything. That is easy to show. You can cook up some p-adic integers with with norm one. It's easy that you can do. So this sits inside this, and that is compact. This is a proper subset, and the reason why this is not compact is the proper way to say that would be that this SZ is actually dense in ZP. Okay, and that is because ZP is the completion, right? And completion means that the original space will be dense in that space. So it's a dense proper subspace. So it cannot even be a closed subspace. So it cannot be compact. So yeah, so we just learn that the unit sphere is not, yeah, but yeah. So we are getting something which hints us that R with any norm may not be compact. That's I sorry, may not be complete. Yeah. Yes. Yes. Yeah. Now the obstruction that we're facing is, can we extend the p-adic norm somehow to R? Yeah. Then we are, yes. Then we will have a counter example. Right, that is easy. So when you take m by n, then you define the period to the minus VPM plus VPN. Hmm. Yeah, so one of them would be zero. That's fine. Yeah. Yeah, one of them would be zero, but that's fine. Yes, because I don't know how to. Because the norms you can take and you can think if they converge, then you can put that norm. I don't know. This is yeah. Because yeah, this will be very strange. Because if you just take a Cauchy, because if you take a point in R, then you take a Cauchy sequence converging to that, but then that may not be a Cauchy sequence in the p-adic norm. So it may not be. Yeah, it's quite strange. Strange things. Yeah. So I mean, we have done the standard part of the problem, but yeah, I don't know if any two norms induce the same topology. But again, from the perspective of functional analysis, it kind of suggests that. No, so what functional analysis kind of thing suggests me is the following. Yeah, maybe I should write that because that you can see. So then maybe we can just see. So let v this okay be complete. Let's just assume completeness. Okay, complete normed space v be uh, finite dimensional. Then the claim is so at least by assuming completeness can be proved that the sphere is compact. Yeah, yeah. Just think about it. I'll just come in a minute. Right. Exactly, yes. Yes. Because then the convergence of the Cauchy sequence comes from completeness, or like you said about the nested interval. But now we need to get to a Cauchy sequence. And there I think you can we can use the finite dimensionality. Yes, maybe it's a good idea to write that. And technically, this is also called something called totally bounded, which you can look at read about later. But it's the same thing here. Yes, I think I have not written the question very clearly. I realize over R. Okay. And let me write here with the usual topology. Okay. Now, so R has the usual topology. That's all I've said. I'm not saying V anything about the topology of V. Now it should be okay. Now it should be okay. So the question would be that from V to uh, R, Rn. Okay, this is just my way of thinking. Yes. So now you can show now you can show that this thing is homeomorphic to Rn. Now you see, now if the topology is same, then then all the norms are same on Rn. That we have proved. So if you use that, then this we can show. And this is easy because, for example, if n is equal to 1, then you just fix a non-zero vector as I just checked. So you take, I mean, I was just rough checking in rough, take this. And you can show this is a continuous function with a continuous inverse. Okay. And in general, if you take a basis, then you just take a linear map and so on, and you can show it is continuous. Okay. So that you can do that. So that will not be difficult. Why will it be continuous? And the essence is that no matter what the norm is, there are only finitely many vectors which are involved, which will be involved in that map, the basis. And you can take the largest norm of that, right? And then whatever map is like, then it's like a coordinate map, so it's going to be continuous. Yes. Uh, yeah, because it's a norm, so you have to use all the triangle inequality and everything, right? So it will just work. Yes, it will work, and it will be homeomorphic, both sides continuous. Then you are done, right? Then the sphere is compact. So really the point was that putting the what topology on R you start with is the key, right? That is the point. So now we must, so basically the question comes down to R, right? And all these questions, uh, all these questions come down to R. So let me write the two questions which I think finally we can refine out of yeah. So like Rn. So what are the induced topologies? So yeah. So it really comes down to R. Is R oh wait, sorry, just a minute. Yeah. Yeah. Let me write this question. So and I think the answer to this will be no. Maybe do all norms on R induce the same topology? I mean, that question on Rn now reduces to R. If the answer is true on R, then it is true on Rn. Like the question, this question, are the topologies the same? So that really, as we have seen, that comes down to this question. So this is one good question to ask. And yeah, and the other would be, yeah, the other natural question is, which is like the next easy one, means easy sounding. Uh, be finite dimensional. All right, and the answer to this is yes. So let me just mention that. Yeah, that's why it sounded easy. So let me mention one thing here to you. So like you see, Aryan, so on page 5, what I wrote here, the complete condition. You see, now it is actually redundant because while proving the homeomorphism, you don't actually need completeness. Yeah. So the sphere is compact if you assume if it's finite dimensional over R. So yeah, with the usual topology. So really, the key burning the main question is, what are the norms on R, and do they induce the same topology as the usual one? Okay, and if not, then what are those topologies, and is the sphere compact with respect to those topologies? Okay. If the answer is yes, then on Rn also the sphere will be compact because product of compact sets is compact. A kind of. Hmm. It is compact if we assume the topology to be that. That's why I'm asking this question whether all the topologies are the same. If they are, yeah. So this the compactness is the topological condition. It's not even dependent on the metric. So if you can prove that the topologies are same, basically I'm saying that this is the only question we need to worry about. Right? If we can, if the answer to this is yes, or if not, then if not, then is this unit interval compact? Okay, and when we say R here, we should really say that R uh, as a field with the usual order. That's all. We are not putting the topology as yet. We want to just put norms now and see if it becomes a what are the topologies that we can get. Right? We don't want to throw out everything. We don't want to throw out the order. Otherwise you can put any. Otherwise there will be other topologies. I think because then it just becomes a set and or it's not a set. It's a field yet still. But we want to keep this at least this much we want to keep so that we can talk about unit sphere and well I mean unit sphere you can still talk about without having an order. But let's put this and probably this will and make the question easier definitely just to state. So I don't know. So think about this and yeah, maybe you try to uh, think and maybe you can already look online or something and find something and read or something. Tell me, right? Maybe next time. Yeah, yeah. You just explore this because I think you can find some interesting things and you can yeah by yourself or whatever. But just you can share it with me, right? Yeah. Advanced. Yeah, so maybe you can ask your professor also. So on R, if yeah, are all this question, you can ask him and see what he says. Yeah. Okay. I've okay. That's no, that's nice. Okay, so you're going there as for teaching. Okay, okay. That's nice. That's nice. Okay. Yes, yes. That's I think I've heard of that camp and I think it's quite good. May uh, okay. Right. Let me just have a look at the camp because I think once someone had also sent me uh, epsilon delta. Okay, epsilon India. Epsilon India math camp. Mm-hmm. Mm-hmm. Yes, I think this is certainly yeah nice and Prayoga Institute of Education. Yeah, man, this is going to be great, of course. Right, yeah, yeah, sorry. So I should just. Oh, yes, yes, from there actually I had got. Yeah, and that is a good place. Right, right. Okay, yeah. Hmm. Huh. Huh. Okay. Yeah. The number theorist. Karndikar is there. Prithviji is there. Yes, he's also quite good actually. Yeah, this guy is also very good. Okay, Aditya Karnataki. Yeah, he's a very good number theorist. He's a number theorist, and I don't know about this lady from Harvard. And KV Subramaniam. Okay, he's also here. Okay, so this KV Subramaniam was my advisor for my MSc. So yeah, he knows me. He would know me my name. Yeah, and Pradeep Srinivasan. I don't know him. I don't know Rajiv Gandhi. Yes, I don't know these people. Of course, that's yeah, but yeah, of course, it's going to be great. I mean, yeah, you should. It's opportunity is yeah one of huh? Yes. So I mean, yeah, you should decide. But I think I don't know that you can decide. I mean, anything is. But once you decide, then you can yeah maybe you should decide before the interview result comes out. And before the dates come, and you should decide the priority whether if it clashes, then what are you going to choose? In an Okay, then it's clear. Then there is then there is no worry actually because you know what you have to do. I mean, then it's fine. Yes. Hmm. Yes. Right. Yeah. But make sure you keep practicing the MCQs and so on. Yeah. Huh. Yes. 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 That's good. Yes. Because you see, to some extent, it is like a JE thing. To some extent, in the sense that it's not all about understanding mathematics and things and being creative and so on. It's also about having speed, right? So and you want to clear the exam, so you have to do what it takes, and that's all. That understanding is enough. Once you have that, then you will do the right thing. Yes, yes, it's practice. Even if they're easy questions, you have to just do them quickly. That yeah, like for example, maybe like this, there are AIME questions and so on. I mean, I don't know, if you think that they are useful, you can look at them. So AIME 10, but it is 12 also maybe. Yeah. So like towards the last 10 problems, if you look, or toward even last 5 problems, try to set some timer and do it. Those. Yeah. And then like that, there will be many exam like HMMT, so Harvard Math Tournament, something like that. So there are these kind of not so difficult questions, but you do them quickly. Yes, yes, yes. But Putnam questions are not going to may not be very useful for the objective part. Okay, that is a thing. Yes, may, yes, it's more undergrad. Yeah, so that's my point. That you have to know all those trigonometric identities, tricks, and not just know, but bring them out quickly when needed. So you should do that, and all of them have their merits. Okay, it's not a waste. Yeah, all those small like trigonometric identities we prove, they tell us about the patterns, right, that can exist and so on. So later when you learn, and like I'm learning and I will learn more, hopefully, like Fourier analysis, harmonic analysis, then these trigonometric functions come again and again. Or say, like even the fractional part of it, there are many tricks and things about them, but they keep coming up later also. Okay, so yeah, yeah, yes, 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 yeah. Practice, like in the sense that even if you do easy questions, that's fine, but do some large quantities of them. What to do? I mean, you have to do them, and it's not bad. Yeah, no, doing things quickly is also important, right? For example, if you are in a class, so for example, if you are in a certain kind of class where you're learning a new topic, but it involves a lot of calculations of checking small things, right? Then the professor just says that, is it obvious? So the calculative part. But if you're quick in calculations, then you can just check it quickly, then you can move with the flow more easily. Otherwise you will say, okay, I'll check it later, like I have one that habit. So all these things are going to make you a more complete mathematician. Yeah, because mathematics is also about speed at some to some extent, like sometimes to get something done, you have to have speed also, which I'm not saying you don't have, but if you just practice and practice, just keep running, keep practicing till the exam. Yeah. Yes, yes, and it will help you always in life. Okay, so this is a very great opportunity, so you should do it. And yes, 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 but this is a good thing. And think about that question, the topologies that we can put. That I think that that question can actually lead to interesting, yeah, things. Yes. In fact, just the last thing I can mention that. So what we did today was like if R is if you put R the usual topology, if you take a finite dimensional vector space and the sphere is compact, right? What you can prove, though this may not be easiest thing to do, if V is not finite dimensional, then the sphere is not compact. That's a non-trivial theorem, but you can try to prove it, and you can ask a professor about this. Maybe he can give you some interesting, yeah, that. So the sphere is, so basically finite dimensionality can be characterized by the sphere being compact. That's the equivalent. Yeah, yeah. So basically the finite numbers are those numbers for which the normed vector spaces a sphere is compact. Finite numbers can be written in this language. Okay. Yeah. And that is a very interesting problem actually. Yeah. But everywhere we are assuming that the base field R has a usual topology. Now the question is, yeah, is that always true for any? Exactly. Can you put a norm for which the topology is not usual? I do not know. You should search it out or ask. Tell me. Okay. Okay. Nice. Okay. Bye. Take care.